Welcome to ATMOS 5000, day 37. Our objectives today are being pulled from Chapter 9, sections 9.1 and 9.2. Specifically, we're going to be looking to see how we do sea level pressure reductions from station pressures, and then we'll look at how weather data is transmitted through a process called METAR decoding. So we have sea level pressure reduction here. So when we measure the pressure at an altitude that's above mean sea level, there is a procedure that can be used to convert it to a standard sea level pressure so that you can create a sea level pressure map. And it's the way that we do that is that the pressure at mean sea level is equal to the pressure measured at the station times the exponent of the ratio of the height of the station over a constant A times the average virtual temperature of the layer between the station and sea level. Well, this constant A is just R sub d over G, which is 29.3 meters per degree Kelvin. But how do you define a virtual temperature for a layer between the station and sea level when all of that area is essentially underground? So the way that we actually do that is we take the virtual temperature at the initial time at the surface, measured at the station height, plus the virtual temperature 12 hours earlier, measured at the surface, and then you add to that the standard atmospheric lapse rate of 0.065 K per meter times the height of the station in meters, and then multiply that whole thing by 0.5. So what we're doing is we're assuming that the atmosphere between the station and sea level, the temperature decreases at the average standard atmospheric lapse rate of 0.065 K per meter. So METAR code is the most common format in the world for the transmission of observational weather data, and it's been standardized through the International Civil Aviation Organization, and these METAR codes can be understood around the world. They make a lot of simplifications and a lot of code to try and minimize the number of characters that are actually used in the transmission of the data. And that's a holdover from the old teletype machines that people used to use to do this. So what we have here is we have an example of weather data that has been encoded in the METAR code, and we're going to go step by step on how to interpret this code and what all of the different symbols and all of the different abbreviations mean. So every METAR starts off with a 4-letter location identifier. These are typically done at airports, so this will usually be the airport code, and the first letter usually is the continent code. And so for Chicago Midway International Airport, which is what this METAR is for, it's KMDW. The second group is actually talking about the day of the month and the time that the observation is valid for. So they don't identify the month, they don't identify the year. That if you want to archive these METARs, you have to keep that information separate because it's not part of the METAR record itself. So what we have here is the first 2 digits are the day of the month. So in this case, it would be the 14th day of the month. And then the next 4 digits are the time in UTC. So in this case, 2353 Zulu. These standard METAR observations are always completed in the last 10 minutes of the hour. So sometime between, in this case, would have been 2350 and 24. So they always try and do that during the last 10 minutes of the hour. The next group is the wind coding, and there can be lots of different information there. The standard part of the wind coding is the first part, which is the wind direction in tens of degrees from true north and the wind speed in knots. So the 15013 The 150 would be the wind direction, so that's 150 degrees. 13 would be the wind speed in knots. And then this one happens to have a G21 after it, and that just means that the wind is also gusting to 21 knots. And then sometimes if you have a variable wind that is meandering more than 60 degrees, you'll have this V code, and it will essentially show the degrees at which the wind is varying between. So in this case, the wind happened to be varying between 120 degrees and 180 degrees. The next group of code is the present weather. This isn't always there. If there's nothing going on, then this area would just be blank. But we can basically describe the present weather as rain or frozen precipitation or precipitation of unknown type or fog, freezing fog, mist, haze, squalls, thunderstorms, funnel clouds, hail, small hail, all these sorts of things. So in this case, we have the identifier, in this case rain, RA, and then we can have a plus, a minus, or no sign. So a minus would be light rain, no sign out in front would be moderate rain, and a plus out in front would be heavy rain. And then we have BR, which is mist, which is different than drizzle, but this group is the prevailing visibility in statute miles. So this will only report up to 10 statute miles, and if it says 10 statute miles, you interpret that as the visibility is greater than or equal to 10 statute miles. Think about that from a pilot's perspective. If the visibility is greater than 10 miles, they don't really care, but they do care if the visibility is 2 miles or a half a mile or 3.5 miles. Those differences make sense. So in this case, we have a 4 statute mile visibility, and they can report fractional visibility. So you can have like 1.5 miles or 3/4 of a mile or 1/4 of a mile, and values that are less than 1/4 of a mile will be reported as M less than 1/4. So here we have the cloud amount and height. So we've already done this before when it came to the celestial dome for clouds. So here we have a broken cloud deck at 2,700 feet above ground level. And recall that broken means that you have coverage between 5/8 and 7/8 coverage. And then we have an overcast layer at 4,300 feet above ground level. And overcast, of course, is 8/8 coverage. Remember that you can have clear skies, which would be CLR. You could have few clouds, or you could have scattered clouds, depending upon the situation. The next grouping is the temperature and dew point temperature. Each is reported in whole degrees. So this would correspond to a temperature of 8 degrees Celsius and a dew point temperature of 4 degrees Celsius. If the 4 had been -4, there would have been an M04. Then that would indicate that the temperature is minus. The next grouping is the altimeter setting. It's always predicated with an A in the front, and it's reported in inches of mercury. So this happens to be 29.74 inches of mercury would be the altimeter setting. Next we have a bunch of remarks. So RMK is the beginning of the remarks section, and this time we have AO2, A02, which is AO2, which is basically saying that this is an automated station that has a precipitation discriminator, so it can tell from the different types of precipitation, whether it be frozen or rain or freezing rain, that sort of thing. And then this one also happens to have information about the peak wind. The peak wind in this case is at 140 degrees at 27 knots. So that's where the 14027 comes from. And then you have a slash, and then you have the time at which that peak wind occurred. In this case, it happened at 23:27 Zulu. So that peak wind is reference to what happened in the last hour only. And there can be lots and lots of different remarks that can be here. You can have information about lightning, you can have information about towering cumulus clouds, you can have funnel clouds, you can have blowing dust, you can have blowing snow. Basically any observation that doesn't fit nicely into the standard METAR codes would show up in the remarks section. Next, we have the sea level pressure in hectopascals, tens, units, and tenths. So in this case, what we've done is we've lopped off the first digits, the 10 or the 9. Sea level pressure is going to be 1007.9 hectopascals. Next, we have the hourly precipitation amount in hundredths of an inch since the last METAR. And if it's a trace of precipitation, it would just be labeled as P0000. In this case, we have P0002, which means that we had 2 1/100ths of an inch of precipitation in the last, or since the last METAR, which is basically in the last hour. There are also precip codes that are not in this one that would show the precipitation amount in the last 3 hours, the last 6 hours, and the last 24 hours. Those are additional codes, groupings that could show up in a METAR. Next, we have the hourly temperature and dew point in tenths of a degree Celsius. So this gives you a little bit better information about the temperature, and this is used primarily for climate recording. So T tells us that this is the hourly temperature, and then we have a temperature of 7.8 degrees Celsius. And basically the first digit after the T is going to be a 0 or a 1. If it's 0, then it's going to be a positive temperature. If it's 1, it's going to be a negative temperature. So we have temperature, 0 indicates it's positive, and then we have 078, and so that corresponds to 7.8 degrees Celsius. Then we have the next group, which is the dew point temperature. The first digit is a 1, so that means that it's going to be a negative dew point, and then it happens to be 3.9 degrees Celsius, so minus 3.9 degrees Celsius. The next group, starting with a 1, is the 6-hour maximum temperature in tenths of a degree Celsius. So the 1 indicates that it's the 6-hour max temperature. The next digit, which is currently a 0, indicates whether or not it's positive or negative. And then you have the temperature in tenths of a degree Celsius. So this is positive 7.8 degrees Celsius. The next group, which is the 2 group, is the 6-hour minimum temperature. So once again, the next digit after the 2 is the 1, so that's a 0 or 1. It's positive or negative. In this case, it's going to be negative. And then we have 5.6 degrees C, so the 6-hour minimum temperature has been minus 5.6 degrees C. Here we have the 5 group, which is the pressure tendency. So we have 5, which tells us the pressure tendency. A is a character that corresponds to the different types of pressure, and you have to look that up in a table. So we have character code number 6, and character code number 6 actually means that the 3-hour pressure tendency is falling, then steady. That's code 6, and you'd have to look that up each time unless you memorized it. And then we have the pressure tendency in tenths of a hectopascal in the past 3 hours. And so from code number 6, we know that the tendency was falling, so it's going to be minus, and then it's going to be 3.2 hectopascals. And then you'll often see this little $ at the end. That's just a maintenance check indicator that says that the automated surface observing system needs maintenance. It doesn't mean that the data is invalid. It just means that there is something that the algorithms have identified with the system that will need maintenance soon.